Welcome to the GC Most Important Q&A, your complete guide to mastering gas chromatography concepts. This presentation is designed by Pharma, where science meets clarity. We'll walk through the fundamentals, instrumentation, columns, detectors, and safety applications. So, grab your notebook. We're about to make GC simple, practical, and memorable. Contents. Here's the roadmap for today's session. We'll begin with fundamentals and theory, then move to instrumentation and columns and phases. Next, we'll explore detectors before finishing strong with applications and safety. Each part is packed with examples and clear explanations to strengthen your chromatographic understanding. Fundamentals and theory. Let's start with the foundation of gas chromatography, the basic science that makes everything else possible. Understanding these core principles will help you troubleshoot, interpret data, and master system design. Each concept toward confident real-world analysis. So, let's explore science on every GC peak. What is gas chromatography? Gas chromatography, or GC, is a powerful analytical technique for separating volatile compounds. It uses an inert carrier gas and a stationary phase to achieve precise separations. This allows both qualitative and quantitative analysis of complex mixtures. In short, it's the backbone of purity testing. The basic principle of GC. Now, let's talk about the basic principle of GC. It's all about repeated vaporization and condensation between a gas phase and a stationary phase. Samples are injected, separated, and detected as they travel through the column. Each component's unique travel time, or retention time, tells us exactly what's in the sample. Define retention time. Retention time, or TR, is like each compound's personal fingerprint in a chromatogram. It's the time from injection until that compound's peak appears. Under fixed conditions, it's a key indicator of identity and consistency. Knowing retention times helps analysts confirm compound identities with precision. What is the partition coefficient, K? The partition coefficient defines how much a compound prefers the stationary phase versus the mobile phase. A higher K means stronger attraction to the stationary phase and therefore longer retention. It's a simple but vital parameter controlling separation efficiency. Think of it as the stickiness factor, deciding who leaves the column first. GLC versus GSC, a tale of two phases. Here's an interesting comparison. Gas-liquid versus gas-solid chromatography. GLC uses a non-volatile liquid stationary phase. GLC relies on a solid adsorbent like silica or alumina. GLC separates by partitioning. GSC separates by adsorption. Both have unique strengths, and choosing the right one depends on your analyte type. Carrier gas must be inert. The carrier gas is the lifeline of your GC system, but it must stay chemically inert. This prevents unwanted reactions that could ruin accuracy. Helium and nitrogen are commonly used because they simply carry the sample without interference. In short, a pure, inert carrier gas means reliable and reproducible results. Factors affecting retention time. Retention time depends on several parameters. Higher column temperatures and faster gas flow reduce retention, while stronger stationary phase interactions increase it. Compound volatility also plays a big role. More volatile compounds exit faster. Mastering these factors helps you fine-tune your chromatographic separation perfectly. Define peak area. The peak area is the heart of quantitative analysis in GC. It represents the total signal under a chromatographic peak. Since it's proportional to concentration, it's used to measure how much of each compound is present. Simply put, peak area equals quantity. What is a chromatogram? A chromatogram is your analytical story, a visual plot showing detector response over time. Each peak represents a compound eluting from the column. It's the fingerprint of your sample composition. Learning to read and interpret chromatograms is key to analytical success. Why normalize peak areas? Normalization helps correct for injection or detector variability. By adjusting all peak areas to sum to 100%, it provides accurate composition percentages. For example, peaks of 120, 85, and 95 normalized to 40%, 28.3%, and 31.7%. It's a simple yet essential practice for reliable results. Instrumentation. Now, let's move on to instrumentation, the mechanical soul of your GC. Understanding each component ensures smoother operation and fewer troubleshooting nightmares. From injectors to detectors, every part plays a critical role in precision. Let's explore how the machine works together as one analytical system. List main GC components. A GC system includes 4 major components: carrier gas, injector, column, and detector. These parts work in harmony. The carrier gas moves the sample, the injector introduces it, the column separates it, and the detector quantifies it. Each part must be clean, calibrated, and well-maintained. Together, they form a powerful analytical engine. Why heat the injection port? The injection port is heated to vaporize samples instantly. This creates a sharp, narrow band of analyte entering the column. The result? Better resolution and consistent reproducibility. It's a small detail that makes a big difference in analytical quality. Explain split injection. Split injection helps manage concentrated samples. Most of the sample is vented out to avoid column overload. Only a small portion enters the column for analysis, giving cleaner peaks. It's the go-to method when precision outweighs quantity. When to use splitless injection. Splitless injection is your best friend in trace analysis. Here, the entire sample enters the column for maximum sensitivity. It's ideal for low-level or high-boiling analytes like pesticides or residues. When every nanogram counts, go splitless. Cold on-column injection. This technique deposits the sample directly into a cool column. It's then gradually heated to vaporize the analyte. This gentle approach prevents thermal breakdown, perfect for sensitive compounds. You get accuracy, reproducibility, and no burnt peaks. What is PTV injection? Programmed temperature vaporization, PTV. Injection starts cool and heats rapidly. This flexibility supports both split and splitless modes. It minimizes contamination by preventing non-volatile residues from entering the column. PTV combines precision, versatility, and sample protection in one design. Control oven temperature. Why? Precise oven temperature control is the secret to reliable separations. Even a small drift can change retention times and ruin resolution. That's why modern GC ovens maintain stability within plus or minus 0.3 degrees Celsius. Consistency here means every peak appears exactly where it should, every single time. Constant linear velocity mode. Constant linear velocity ensures your carrier gas flows smoothly, no matter the temperature. It keeps analyte separation efficient and reproducible from run to run. Think of it as cruise control for your GC system. This mode helps maintain performance and accuracy across variable operating conditions. Electronic pneumatics. Why? Electronic pneumatic control, or EPC, automatically adjusts inlet pressure for perfect flow. It compensates for viscosity changes due to temperature shifts. This leads to consistent retention times, peak areas, and better reproducibility. EPC is like an autopilot for your GC's pressure system, smart, precise, and dependable. What is backflushing? Backflushing reverses the flow after light compounds elute. This helps sweep out heavy residues in a single step. It protects the detector and shortens analysis time significantly. A simple flip in flow direction can save hours of cleaning and downtime. Columns and phases. Now we enter the heart of GC performance. Columns and phases. Columns determine how well your compounds separate and how clean your peaks look. Choosing the right type, polarity, and length is crucial for accuracy. Let's dive into the science behind column efficiency. Packed versus capillary columns. Packed columns are short and strong, great for large sample loads but less efficient. Capillary columns are longer, thinner, and offer sharper resolution with smaller samples. Your choice depends on the balance between capacity and precision. Most modern labs prefer capillary columns for their speed and separation power. What are WCOD columns? Wall-coated open tubular, WCOD, columns are the gold standard of capillary designs. They have a thin film of liquid stationary phase bonded to the inner wall. This gives them incredibly high efficiency and broad application range. When accuracy and resolution matter most, WCOD is your best choice. Define Scott columns. Support-coated open tubular (SCOT) columns have tiny particles on the wall to hold the stationary phase. This design increases sample capacity while maintaining decent efficiency. They're a middle ground between packed and WCOD columns. Perfect for when you need both sensitivity and sample tolerance. How to choose column polarity. Column polarity must always match your analyte's chemistry. Use nonpolar columns for hydrocarbons and polar columns for alcohols or acids. Polarity controls how compounds interact with the stationary phase. Get it right, and your separation will be smooth and clear every time. What is film thickness? Film thickness affects how long compounds stay in the column. Thicker films retain volatile compounds longer, improving resolution. Thinner films handle high-boiling analytes faster and with greater efficiency. Choosing the right thickness is like tuning your GC for speed versus sharpness. Why use fused silica? Fused silica columns are the industry favorite for good reason. They're chemically inert, flexible, and thermally stable at high temperatures. Their smooth inner surfaces prevent peak tailing and sample adsorption. If you want durability with precision, fused silica delivers both. What determines column length? Short columns, 10 to 15 m, are ideal for quick cooking. Used general analysis. Long 60 m columns handle complex mixtures with high resolution. Longer length means better separation, but at the cost of more time. Internal diameter impact. Smaller internal diameters give sharper peaks and faster runs, but require careful injection. Wider columns handle larger sample loads with slightly lower efficiency. It's all about the balance between capacity and resolution. Choosing the right ID ensures your GC system runs optimally for your workload. What is column bleed? Column bleed is the silent background noise in your chromatogram. It comes from the stationary phase degrading under high heat. You'll see it as a rising baseline that can mask trace peaks. To avoid it, use low bleed columns and condition them properly before use. When to use a guard column? A guard column acts as your analytical column's bodyguard. It traps non-volatile residues and particles before they can cause damage. This simple addition extends column life and keeps maintenance low. If you value consistency, always protect your main column with a guard. Detectors. Now we move to the sensory organs of GC, the detectors. They transform separated analytes into measurable signals. Choosing the right detector defines what kind of information you can extract. Let's see how each detector type brings something unique to the table. What does TCD measure? The thermal conductivity detector, TCD, compares heat flow between carrier gas and analyte. It's universal and non-destructive, responding to almost all compounds. Because it measures differences in thermal conductivity, no compound escapes unnoticed. TCD is reliable, simple, and ideal for permanent gases or mixtures. Why use helium with TCD? Helium is a favorite carrier gas because of its high thermal conductivity. This makes even small analyte changes easily detectable. It enhances baseline stability and detector sensitivity. In TCD systems, helium keeps every signal crisp and clear. FID selectivity explained. The flame ionization detector, FID, responds specifically to organic compounds. It detects carbon-hydrogen bonds by creating ions in a tiny hydrogen flame. It ignores inorganic gases like CO2 or H2O, making it highly selective. If it burns carbon, FID will catch it. How does ECD work? The electron capture detector, ECD, uses beta radiation to emit electrons. When electronegative compounds capture these electrons, the signal drops. That drop tells you how much of the compound is present, even in parts per billion. ECD is your go-to for detecting halogens, pesticides, and pollutants. What is NPD or FDD? The nitrogen phosphorus detector, also known as the flame thermionic detector, is designed for selective detection. It uses a heated rubidium bead to form ions when nitrogen or phosphorus compounds pass through the flame. That makes it perfect for pesticide or fertilizer residue analysis. In short, NPD gives you high sensitivity exactly where you need it most for N and P compounds. When to use FPD? The flame photometric detector, or FPD, shines when it comes to sulfur and phosphorus detection. It uses specific wavelength filters, 394 nanometers for sulfur and 526 nanometers for phosphorus. It's incredibly sensitive, even down to parts per billion. Whenever your target is sulfur compounds or phosphorus additives, FPD is your go-to detector. What is BID? The barrier discharge ionization detector, BID, is like a universal eye for your GC. It creates a 17.7 electron volts helium plasma that ionizes nearly every compound except helium and neon. This gives you sub-ppm sensitivity across a wide range of analytes. It's as close as you can get to mass spectrometry performance without the cost and complexity. Why couple GC with MS? GC separates while MS identifies. Together, they're a dream team for unknown analysis. GCMS combines the precision of chromatography with the molecular insight of mass spectrometry. It confirms peak identity and enables trace detection down to ppb levels. That's why it's known as the gold standard for analytical detection in research and quality control. Minimum detectable amount, MDA. Each detector type has its own detection limit, known as the minimum detectable amount. TCD can detect around 10 ppm, FID reaches 0.1 ppm, and ECD goes as low as 0.01 ppb. FPD, BID, and MS all push sensitivity even further depending on setup. Knowing these limits helps you pick the right detector for your target analyte. How to select a detector? Choosing the right detector is all about your analyte and purpose. TCD works universally. FID loves hydrocarbons, ECD focuses on halogens, and NPD targets nitrogen and phosphorus. FPD detects sulfur and phosphorus odors, while MS handles unknowns and complex mixtures. Each detector has its specialty. Use the one that speaks the language of your analyte. Applications and safety. We've now reached the final chapter, applications and safety in GC. This is where theory meets practice, covering real-world uses across multiple industries. You'll see how GC ensures quality, safety, and compliance across pharmaceuticals, food, and energy. Let's explore where GC truly makes a difference. Key GC application industries. Gas chromatography plays a vital role across industries. In pharmaceuticals, it checks residual solvents. In food safety, it monitors pesticides and authenticity. Environmental labs use GC for air, water, and soil analysis, while petrochemical and polymer industries rely on it for composition and additives. Wherever purity and precision matter, GC is there. Analyze residual solvents. Residual solvent testing ensures that pharmaceutical products meet safety limits. The sample is dissolved, analyzed via static headspace, and quantified using FID or MS detection. This technique isolates volatile solvents efficiently and cleanly. Following USP guidelines ensures both accuracy and regulatory compliance. What is static headspace? Static headspace analysis collects vapors above a sample after equilibrium. It's simple, clean, and avoids matrix interference during injection. Only the volatile fraction enters the GC column for analysis. It's perfect for detecting solvents, VOCs, and impurities with minimal sample handling. Explain dynamic headspace. Dynamic headspace, or purge entrap, pushes sensitivity even further. An inert gas purges volatiles from a liquid into a trap, which is later heated to release analytes into the GC. It can achieve PPT-level sensitivity for ultratrace analysis. When low concentrations really matter, dynamic headspace delivers unbeatable precision. Thermal desorption principle. Thermal desorption is ideal for air sampling and VOC monitoring. Collected vapors on sorbent tubes are heated under helium flow to release analytes. A cold trap focuses them into a sharp injection band for analysis. This method concentrates samples, enhances sensitivity, and ensures cleaner chromatograms. Handle pyrolysis samples. Pyrolysis GC helps study polymers and their thermal behavior. A small polymer sample is heated rapidly to decompose it into smaller volatile fragments. Those gases are then analyzed via GC to identify components or additives. It's a smart way to study materials that can't be easily dissolved. Avoid hydrogen leaks. Hydrogen is an excellent carrier gas, but it comes with explosion risks. Leaks can occur easily since H2 is light and flammable between 4% to 75% in air. Always use leak detectors, venting systems, and flow controls for safety. If risks are high, switch to helium or nitrogen as safer alternatives. Joule-Thomson cooling effect. When high-pressure gas expands suddenly, its temperature drops sharply. This Joule-Thomson effect can cause heavy hydrocarbons to condense in sampling lines. To maintain sample accuracy, heated regulators and lines are used. Ignoring this can lead to big errors in gas composition analysis. How to calibrate a GC. Calibration keeps your GC quantitative and compliant. Inject a certified standard, calculate the response factor, and use it to determine unknown concentrations. Normalization to 100% ensures accurate reporting. Consistent calibration equals consistent trust in your data. What is method validation? Every GC method must be validated for reliability. That includes parameters like linearity, accuracy, precision, detection limits, and robustness. Following ICH guidelines confirms that the method is fit for purpose. Validated methods ensure that your results hold up in audits and across labs. Congratulations, you've completed the UNA Power Pack. From principles and columns to real-world applications. If you found this session helpful, don't forget to like, share, and subscribe to Pharma Talks for more pharma and analytical learning. Stay curious, keep testing, and see you in the next masterclass. Thanks for watching.